Very good morning, students. So today we will talk about the simple harmonic motion. Okay. In previous lecture, we have discussed about the basic introductory terms. Okay. So now we will discuss about the simple harmonic motion. So first of all, we should aware what is the definition of the simple harmonic motion. So as you can see, simple harmonic motion SHM is defined as a motion in which the restoring force is directly proportional to the displacement of the body from its mean position. Okay. Now the direction of this restoring force is always towards the mean position, and the acceleration of the particle executing the simple harmonic motion is given by the acceleration minus omega square xt. And here you can see omega will be the angular velocity of the particle. Okay. So let us suppose consider a particle oscillating back and forth about the origin of an x-axis between the limits of plus a and minus a. And this oscillatory motion is said to be simple harmonic if the displacement x of the particle from the origin varies with time as xt equal to a cos omega t plus phi. So the simple harmonic motion is not any periodic motion, but one in which the displacement is the sinusoidal function of the time. Okay. Now in the sinusoidal motion, each interval of the time, let us suppose for the t by 4, where t is the period of the motion, so it gives the values of the displacement as the continuous function of the time, and the quantities of capital A, omega and phi which characterize given the SHM have the standard names like the acceleration, angular frequency and phase. Okay, so we can say xt, that will be the displacement, x at the function of the time t, capital A will be the amplitude, omega will be the angular frequency, and omega t plus phi, that will be the phase, that is time dependent. Okay, and the phi will be the phase constant. So first of all, we should aware about the simple terms, that is what is simple harmonic, what is periodic, and what is the oscillation motion. So we can say that simple harmonic motion can be described as an oscillatory motion in which the acceleration of the particle at any position is directly proportional to the displacement from the mean position. It is a special case of the oscillatory motion, and all the simple harmonic motions are oscillatory and also periodic, but not all oscillatory motion are SHM. Oscillatory motion is also called the harmonic motion of all the oscillatory motions, wherein the most important one is simple harmonic motion. In this type of the oscillatory motion, displacement, velocity and acceleration and force all are vary with respect to time in a way that can be described by the either sine function or the cosine function, that is collectively called the sinusoids. Now we can say that the study of the simple harmonic motion is very useful and forms very important tool in understanding the characteristics of the sound waves, light waves and the alternating currents. Any oscillatory motion which is not simple harmonic can express as the superposition of the several harmonic motions of the different frequencies. Okay. These are some differences between the periodic oscillation and the simple harmonic motion which we should be aware about it. First is periodic motion. What is periodic motion? A motion that repeats itself after an equal interval of the time. For example, we can say uniform circular motion. There is no equilibrium position. There is no restoring force. Also, there is no stable equilibrium position. That is a very important point, and we should remember about it, that there is no stable equilibrium position in the periodic motion. Okay. Now let's discuss about the oscillation motion. So to and fro motion of the particle about the mean position is called an oscillatory motion. That is, particle moves on either side of the equilibrium mean position. That is an oscillatory motion. It is a kind of the periodic motion that is bounded between the two extreme points. For example, we can say oscillation of the simple pendulum, spring mass system. Okay. In the oscillation motion, the object will keep on moving between the two extreme points about the fixed point. That is called the mean position or the equilibrium position along any path, the path that is not constant. There will be a restoring force directed towards the equilibrium position to the mean position. So in an oscillatory motion, the net force on the particle is zero at the mean position, and the mean position is a stable equilibrium position. Okay, this is the definition of the oscillatory motion. Now let's discuss about the simple harmonic motion or SHM. What is SHM? So that is the special case of the oscillation along with the straight line between the two extreme points. The path of the SHM, that is the constant, The path of the object needs to be straight line. There will be a restoring force that is directed towards the equilibrium position or the mean position. And the mean position is simple harmonic motion, that is the stable equilibrium. These are some conditions for the simple harmonic motion, that is the force vector proportional should be proportional to the minus x vector. Also, the acceleration should be proportional to the minus x vector. Okay, these are some conditions for the SHF. Okay. Now let's discuss about the various types of the simple harmonic motion. So before we discuss about the simple types of the simple harmonic motion, we should aware that the amplitude capital A of the simple harmonic motion is the magnitude of the maximum displacement of the part. Okay. As the cosine function of the time varies from +1 to -1, okay, the displacement varies between the extremes +a to -a. And the two simple harmonic motions may have the same omega and phi, but different amplitudes A and B. Okay. So while the amplitude A is fixed for the given SHM, the state of the motion, that is the position and the velocity of the particle at any time t, is determined by the argument. What is the argument? The function of the argument is omega t plus phi. Okay. In the cosine function, this time dependent quantity, that is omega t plus phi, is called the phase of the motion. And the value of the phase at t equal to 0 will be phi, and it is called the phase constant, or you can say it is the phase angle. Okay. So in the argument omega t plus phi, if t equal to 0, so omega t becomes 0 and the quantity remaining will be phi, and the phi is known as the phase constant, or you can say phase angle. So if the amplitude is known, phi can be determined from the displacement at t equal to 0. And the two simple harmonic motions may have the same amplitude and omega, but that will be the different phase angle. Okay. Now, if we discuss about the various types of the simple harmonic motion, you can see here, there is linear SHM and angular SHM. First, we will talk about the linear simple harmonic motion. Now, what is linear simple harmonic motion? When a particle moves to and fro about the fixed point, you can say the equilibrium position, along with a straight line, then its motion is called the linear simple harmonic motion. For example, spring mass system. These are some conditions for the linear SHM. The restoring force or the acceleration acting on the particle should always be proportional to the displacement of the particle and directed towards the equilibrium position. F proportional to minus x vector or A proportional to minus x vector. Here x is the displacement of the particle from the equilibrium position, F is the restoring force, and A is the acceleration of the particle. Okay. Now let's discuss about the angular simple harmonic motion. When a system oscillates angular long with respect to the fixed axis, then its motion is called the angular simple harmonic motion. Okay. Now these are some conditions to execute the angular SHM. The restoring torque or the angular acceleration acting on the particle should always be the proportional to the angular displacement of the particle and should be directed towards the equilibrium position. That means capital T proportional to theta, or you can say alpha will be proportional to theta. Here capital T will be the torque, alpha is the angular acceleration, theta is the angular displacement of the particle. Okay. Now let's discuss about some more key terms like the mean position, which we have already discussed, that it is the point at which the net force acting on the particle will be 0. Now from the mean position, the force acting on the particle will be, we know that F proportional to minus x and acceleration A vector also proportional to minus x vector. So for the condition at the mean position, we should know that net force vector should be 0 or acceleration should be 0. And the force acting on the particle, that will be the negative of the displacement. So this point of the equilibrium will be a stable equilibrium condition. Now let's talk about the amplitude in the simple harmonic motion. You can see here there is a diagram. There are 2 points are there, A dash and A. A dash represents extreme point and A is the extreme point. Okay. So O is the mean position, or you can say equilibrium position between A and A dash. Here we have assumed O8 is the distance A, and it is the maximum displacement of the particle from the mean position. Okay. Now, if we wants to talk about the time period and frequency of SHM, we all know that the minimum time after which the particle keeps on repeating its motion known as the time period, and it is the shortest time taken to complete one oscillation, and it is also defined as the time period capital T, that is 2 pi upon omega. Okay, and the frequency will be the number of oscillations per second, that is defined as the frequency, that is 1 upon T, and the angular frequency omega equal to 2 pi f, or you can say 2 pi upon T. That is the time period and frequency of the simple harmonic motion. Now let's talk about the phase. How can we define phase in the SHM? Okay, the time period is 2 pi upon omega, frequency is 1 upon T, or 2 pi upon angular frequency is 2 pi upon T. Now what is phase? So if we want to define the phase in the simple harmonic motion, the phase of the vibrating particle at any instant is the state of the vibrating or oscillating particle regarding its displacement and direction of the vibration at that particular instant. The expression position of the particle as a function of the time. So x equal to a sine omega t plus phi, where omega t plus phi is the phase of the particle. The phase angle at time t equal to 0 is known as the initial phase, because when we put value t equal to 0, omega t becomes 0 and only phi is remain. Okay. And if we want to describe the phase difference, the difference of the total phase angle of the two particles executing the simple harmonic motion with respect to the mean position is known as the phase difference. Two vibrating particles are said to be in the same phase. The phase difference between them is even multiple of pi. So you can say del phi will be equal to n pi, where n equal to 0, 1, 2, 3, and so on. And two vibrating particles are said to be in the opposite phase if the phase difference between them is an odd multiple of pi. As you can see, del phi will be 2n plus 1 into pi, where n equal to 0, 1, 2, 3, and so on. Okay. So if we talk about the unit of the angular frequency, then SI unit is radians per second. Since the frequency of oscillation, that is simply represented by 1 upon T, is 2 pi times the frequency of the oscillations, and the two simple harmonic motions may have the same amplitude and phase but different angular frequency. So these all are about the some basic knowledge again, that is what is the frequency, what is the time period, okay, what is the angular frequency, what should be the mean position, okay, what are the conditions for executing the angular SHM, conditions for the linear SHM, okay, and we have discussed more about the SHM basic terms. Students, in our next lecture also we will continue with the SHM, and again we will talk about some few new terms. Okay, I hope आपको lecture पसंद आया होगा. Thank you very much.